2. So here, right. Now we go to the next one. What is the other term that is left out now? What is the other term we have left out? A to B we have found out, no? First one. D to A. We have to find out D to A. Is it not? Right? So what do we have to find out? We have to find out D to A, E dot dx. Is it clear? What can we tell about D to A and D to C? Sorry, D to A and C to B. Both are equal. Is it not? Right? But only thing is we are going to go for a change in here. This is B to C. Now this is D to A. Is it clear? So can I write it as minus En del H by 2? Can we write it that? Yes? D to C is minus of D to A. Can you understand? So what are the starting to be the same? So I am not going to rewrite the steps. It's the same. So we will have D to A, E dot dl is equal to minus En del H by 2. Is it? Now we sum up all the terms. What are the terms we have got? Tell me, integral of A to B, E dot dl. What are the terms we have got? Integral of, and write that first. Integral of A to B, E dot dl plus integral of B to C, E dot dl plus integral of C to B, E dot dl plus integral of B to A, E dot dl is equal to 0. Now tell me all the terms. What is A to B? What is A to B? E tan del W plus B to C, En del H by 2. Right? Then C to D, 0. This term is 0. Why is 0? Because this is a conductor. Right? So that term is 0. The next one, the D to A, minus En del H by 2 is equal to 0. So clear? So this will be getting cancelled. Okay? So finally what we have got? E tan del W is equal to 0. So arriving at the condition, E tan del W is equal to 0. Is it not? E tan del W is equal to 0. So clear? Can del W be equal to 0? Can del W be equal to 0? Go to the diagram and think and tell. Can del W be equal to 0? Yes, sir. Del W cannot be equal to 0. So what is the only term that can be equal to 0 from this relation? E tan will be equal to 0. E tan will be equal to 0. Alright? This is only one part we have finished. We have got the next part. So finally E tan is equal to 0. Thus E at the boundary between the conductor and the free space, between E at the boundary means tangential component, into bracket tangential component. Thus E, take it in bracket tangential component at the boundary between the conductor and the free space, between the conductor and the free space is 0. Is 0. Okay. Now, what is D? What is D? Anybody? Gauss law or any other relations? D?
E by epsilon.
Very good. Or it is epsilon into E. E by epsilon is or D is equal to epsilon into E. Right? So we can write it as D tan is equal to epsilon into E tan. Can I write like that? E tan is equal to epsilon into E tan. When E tan is equal to 0, we have the entire relation will be equal to 0. So E tan will also be equal to 0. Right? Clear? What is D? What is E first? No, before the term E. Electric field intensity. What is D then?
Electric field intensity.
Anybody or some other type? Somebody gave that consideration. The electric flux density. Okay, so D is electric flux density. D is electric field intensity. So E tan is equal to H1 into E tan, which means that the electrical flux density at the boundary is also 0. Is it clear? Right? Now take it out. Take it out the tangential component of the electrical flux density. The tangential component of electric flux density is also equal to 0. Is also equal to 0. Okay, now we find the next one. Dn at the boundary. Dn means what is that? What we mean by Dn? D tan tangential component. Dn is normal component. Dn is nothing but normal component at the boundary. Right? You know Gauss law? Gauss law? Please complete. What is Gauss law? Surface integral of D dot ds is equal to Q total charge. Students, you are going to write your example next week. Surface integral of D dot ds is equal to Q. Right? So first we see for your Gauss law to be defined. I am going to consider a Gaussian surface. So this is the Gaussian surface I am going to consider. This is the Gaussian surface I am going to consider. So what are the areas that will be occupying your Gaussian surface? The top surface, the bottom surface and the lateral surface. So the Gaussian surface, what are the three surfaces? Top surface, consider this. Top surface, bottom surface and another one is lateral surface. Okay, so take it out. Integral of top D dot ds plus integral of bottom D dot ds plus integral of lateral D dot ds is equal to 0. D dot ds is equal to 0. Which surface is inside the conductor? Which surface is inside the conductor? Bottom surface is inside the conductor. When bottom surface is inside the conductor, what can you tell about this? It will become 0. Right? So the integral of D dot ds bottom will be equal to 0. So only two areas that are left out. What is that? Top D dot ds plus bottom D dot ds is equal to 0. So clear? Please follow along with me. Integral of top D dot ds plus bottom D dot ds, lateral plus lateral D dot ds is equal to 0. So not lateral D dot ds is equal to 0. Right. Now, what can you tell about the top area? What is the surface area on the top? What is the surface area on the top? Del S. Delta S or del S. Okay. So I can write it as integral of top D dot ds is equal to integral of top D dot ds is equal to dn del S. Dn del S. Okay? Is it not? Top surface it is del S now, so dn del S. Is it clear? Is it not? Am I right? Now top surface is dn into the area. What is that? Delta S is nothing but your surface area. So we have it as top D dot ds is equal to dn into del S. Okay, right. From Gauss law we know that dn into del S is equal to Q. dn into del S is equal to Q. Is it not? Is it not? Before that I have not given about lateral surface. See, lateral surface, let us assume that del S is equal to 0 here. Del S is equal to 0 here. So automatically the lateral surface will become 0. Okay? So only surface that is left out will be your top surface. That is, Gaussian surface is assumed to be at the boundary, which means that del H is also equal to 0. Okay? Gaussian surface now what you are going to do? You are going to imagine any surface there. So del H is lateral surface will also be equal to 0. So only term that will be left is here. What is that? Top surface, that is dn dot dl. ds is equal, delta s will be equal to your charge. Okay, right. Another expression we have got regarding your charge. What is that? Q is equal to rho s into del s. Q is equal to rho s into del s. Okay, surface charge density into the area is nothing but this your charge. So when I equate these two, what can you tell? What can you tell? dn is equal to rho s. When we arrive at this equation, dn is equal to rho s. So this will be a final expression. The normal component is equal to rho s. Is it clear? Thus, following up, are you able to follow this? What we have done? Once again, come here. We have considered a Gaussian surface in order to find out the dn value. The Gaussian surface will have a top surface, bottom surface, and a lateral surface. Okay, the bottom surface we know that automatically the del s will be equal to 0. But when you talk about the lateral surface, del s is assumed to be equal to 0 because we are going to see only at the boundary. Okay, so boundary means automatically the del s is also equal to 0. Okay, now what is the left of the surface? Only at the top. So top it is nothing but dn into del s. That will be equal to q, the charge enclosed q. But another expression for q is equal to rho s into del s. So equating these two expressions, we have got dn is equal to rho s. Okay, thus the flux leaves the surface. Thus the flux leaves the surface normally, and the flux density is equal to, the surface charge density, and the flux density is equal to the surface charge density. What is meant by surface charge density here? What do you mean by surface charge density here? Now listen here once again. Flux density is equal to the surface charge density. Which is meant by surface charge density here? Rho s. You don't understand? So dn is equal to rho s. Okay. What can I go for another expression? dn is equal to, so properly, dn is equal to epsilon naught into en. Epsilon naught into en. That is equal to rho s. So we have en is equal to rho s by epsilon naught. So this is another expression. en is equal to rho s by epsilon naught. Clear now? So there are two possible questions here in the boundary conditions. Boundary condition between the conductor and the free space. They are asking you to derive the boundary conditions between the conductor and the free space. You have to derive this. Okay. There is another derivation which tells you the boundary condition between two dielectric. Right. Now what we have seen? What is this? What is this? Conductor. What is this? Free space. Between the conductor and the free space, you have to derive this. Okay. Next we are going to see is about the boundary conditions between two dielectric. What do you mean for dielectric? What do you mean for dielectric? Conductor area also will have a dielectric. The free space will also have a dielectric. If such condition occurs, what will be your boundary conditions? Right? So there are two derivations here. Be very clear. They are asking you the boundary condition between the conductor and the free space. You have to write this. Clear? The next derivation what I am going to tell you is the boundary condition between two dielectric. One of the dielectric will be in the conductor area and the other dielectric will be in the, what is this? Free space. It will be in the free space. One will be in the conductor and the other one will be in the free space. We are going to see the derivation. Go for the next one now. The boundary conditions between two dielectrics. Boundary conditions between two dielectrics. Hope all of you have got your books. All of you have got your books now. For electromagnetic. Right, now listen. So let us assume that there are two dielectrics, right? So let me have here one dielectric, dielectric 1, and this is dielectric 2. Dielectric 2. And we are going to consider this as your boundary. We are going to find out what are the relations here. Very important derivation. First, let us find out what your electric field intensity. Okay. So, what is the first step actually? Tell me. What is the first step actually? Integral E. What are the integrals? A to B and not to the right. Please tell me A to B E dot dS plus integral E to C E dot dS plus integral of C to D E dot dS plus integral of D to A E dot dS is equal to 0. So not, but here we don't have any surface to be assumed to be equal to 0. Is it not? Because both the terms are direct. Okay. So we will write it as E1 is equal to E1T. E1T means tangential component plus E1N, that is your normal component, E1T plus E1N. Okay. Similarly, E2 is equal to E2T plus E2N. E2T plus E2N. What do you mean by this 1 and 2? What is that 1 and 2? 1 for the first dialectric and 2 for the second dialectric. Right? E will have two components. What is that? One is the tangential component and the other one will be a normal component. So I have written two equations. So clear? Right. Now, modulus of E1T is equal to E tan 1. E tan 1. Modulus of E2T is equal to E tan 2. E tan 2. Okay. And modulus of E1N is equal to E1N will be equal to E1N. And modulus of E2N will be equal to E2N. These are some important steps what you have to write. So clear? Now we go for one surface. First let me take A to B. Right? A to B. What can I tell about A to B? A to B. What is there here? E tan 1. Is it not? So how many? This is 1 and this is 2. To have a uniformity, directing 1 and directing 2. Okay. So A to B can be written as A to B E dot dl is equal to E tan 1, right? Integral of A to B dl. This is not. Again, this distance is del W, so we have it as E tan 1 into del W. That is integral of A to B E dot dl. Following, take it up. E tan 1 into del W. What is integral of C to D? The same way what we have done already. C to D will be equal to minus E tan 2 del W. Because this is the second variable. Minus E tan 2 into del W. So there, and we have to assume here del H is equal to 0. Del H is equal to 0. Assuming del H is equal to 0. So we have integral of D to A E dot dl plus integral of C to D E dot dl is equal to 0. Right? So combining these two terms, we have E tan 1 del W minus E tan 2 del W is equal to 0. which means that del W, we can remove it. So what is that? E tan 1 is equal to E tan 2. E tan 1 is equal to E tan 2. Is it clear? Okay. So what you have to tell here is that if the tangential components are equal, then the condition is that the boundary is continuous. The boundary is continuous. If the tangential components are not equal, then the boundary is not continuous. That is the inference. Is it clear? Listen carefully. The tangential components are equal, then the boundary is continuous. That is your inference. They are not equal, the boundary is not continuous. Okay, what we have arrived at? What is the final conclusion we have arrived at? E tan 1 is equal to E tan 2. Take it out. E tan 1 is equal to E tan 2. Thus, take it down faster. Thus, E tan 1 thus E tan 1 is equal to E tan 2, okay, which means that the tangential component of field intensity, the tangential component of field and intensity at the boundary in both the dielectric is same and so it is continuous see, and so it is continuous. So what is the condition that is to be satisfied for a boundary condition to be continuous? Ma, what is the condition that has to be satisfied in order that the boundary condition is continuous? No, ma. E tan 1 is equal to the boundary condition. What is the condition at the boundary in order that the dielectrics are continuous in chemistry? What is that? E tan 1 is equal to E tan 2, or the tangential component of the first dielectric, if it intensity E tan 1 must be equal to E tan 2. That is the tangential component of the second dielectric. Is it clear? Right. Now what does we'll go for the next one? Take it out. D is equal to what is D in terms of E? What is D in terms of E? Only for 2 persons are taking class. What is D in terms of E? I am asking. Flux density in terms of electric intensity. Others. D is equal to epsilon naught into E. Is it not? Epsilon naught into E. Now, D tan 1 can be written as epsilon naught into E tan 1. Is it not? Right. Similarly, E tan 2 can be written as E tan 2 is equal to epsilon naught into E tan 2. Right? Now, D tan 1 divided by epsilon naught, right, is equal to D tan 2 divided by epsilon. Sorry, we have this epsilon 1 and epsilon 2 now to distinguish. How did I arrive at this? Anybody think that? How did I arrive at this? Previous condition, what we have done? E tan 1 is equal to E tan 1 by d tan 2 is equal to epsilon 1 by epsilon 2, that is equal to epsilon r1 divided by epsilon r2. Relative permittivity of the first medium divided by the relative permittivity of the second medium. That can also be done. Why? Epsilon can be written as epsilon is equal to epsilon naught into epsilon r1. Am I right? Okay, this is the final. This expression you know, epsilon is equal to epsilon naught into epsilon. So what is epsilon 1? Epsilon naught into epsilon r1. Epsilon naught will be the same in both the conditions. Okay, so epsilon 2 will become epsilon naught into epsilon r2. So epsilon 1 by epsilon 2 will become epsilon cancels, epsilon r1 by epsilon r2. Okay, ma'am? Right? Now what do you infer from this? What do you infer from this? What we have done? Is d tan 1 equal to d tan 2? Is d tan 1 equal to d tan 2? Yes or no? No? Why it is no? Because d tan 1 is equal to epsilon 1 by epsilon 2 times of d tan 2. So what can you tell about the boundary? What can you tell about the boundary? You can tell me. Previous condition is relate panna. Pone condition enna paarthom. Continuous na what is the difference? D tan 1 is equal to D tan 2. But what is the condition here? D tan 1 is equal to epsilon 1 by epsilon 2 into D tan 2. So what is the condition? Boundary is continuous or discontinuous? How many of you say continuous? Nobody? How many of you say discontinuous? Very good. It is discontinuous. Okay? Others it is up to you to learn by yourself. And that is what I did. Take it out. Tangential component of D undergoes. Have you all taken this? Have you all taken this? One more step if you want to take it out. D tan 1 is equal to epsilon 1 by epsilon 2 into d tan 2. It is not equal. It is not equal. It is multiplied by a factor of epsilon 1 by epsilon 2. So it is discontinuous. So clear students? Right? Take it out. The tangential component of D. Have you written that? The tangential component of D undergoes some change at the interface. And therefore D is said to be discontinuous. Now we consider the Gaussian surface and evaluate. Okay, next step. Surface integral of d dot ds is equal to surface integral of d dot ds is equal to q. That is top d dot ds plus bottom d dot ds plus lateral d dot ds is equal to 0. Top plus bottom plus lateral d dot ds is equal to 0. Right? Now, here also integral of lateral d dot ds is equal to 0 since del h is equal to 0. So top surface plus bottom surface. Top surface d dot ds plus bottom surface d dot ds will be equal to dn1 into del s. Top surface will be equal to the bottom surface, so it is dn1 into del s. Top surface of d dot ds is equal to dn1 del s. Bottom surface will be bottom minus dn1 into del s. Take it up. Integral of bottom d dot ds will be minus d1 into del s. So with this we have d1n into del s minus dn2 into del s is equal to q. continuous at the boundary between two dielectric. Next step take down. dN1 is equal to epsilon 1 into d tan 1. dN1 is equal to epsilon 1 into d tan 1 and dN2 is equal to epsilon 2 into d tan 2. D tan 2. So we have dN1, sorry, dN1 by dN2 is equal to